glad to introduce Dan Stilwell. He's a professor from Virginia Tech. He got his PhD from Johns Hopkins in '99, and his research focuses on control and what's the estimation?
Sure.
And his main application area is in autonomous boats. So I'd like to introduce Dan Stilwell.
Thank you. All right, so let me, first of all, thank you very much for this opportunity to speak with you. I was asked to speak a little bit about our Riverine project. So this is a sister project to something that's ongoing here at the Robotics Institute. In our case, we're very interested in the guidance problem associated with running through rivers and doing it from a boat. So this is our project. We want to develop a sensing and autonomy system that enables an unmanned boat to operate robustly in a tropical riverine system. And think of the Amazon jungle basin. Think of thousands of square kilometers, largely unmapped, very dynamic, things change all the time, a really challenging type of system. So the challenges specifically for us are the extremely large environment. This makes some things just very difficult, our inaccurate maps. We must move as fast as possible. So just meandering through the environment is not OK. We really need to go as fast as we can possibly go. We've got surface plus subsurface hazards. A lot of what we're going to run into that could cause us problems are, in fact, not visible. They're below the surface of the water. And finally, for a controls challenge, because things are so complicated, we're going to have to be capable of very agile maneuvers. And for a boat, this is as simple as moving backwards, which is hard to do in a boat. OK, so as background, I thought I'd take just a few minutes and show you the other things we do in my lab. And my motivation is that most of what I spend my time on is the very few things that Carnegie Mellon isn't the very best in the world in. So I spend a lot of time on maritime robotics. And so we spend about half our time building cool robots and deploying them in the ocean and other places. And then we spend our other half of our time doing more fundamental research. I know you're familiar with both. We've done things where we have this up in the upper left-hand corner where it says multi-vehicle experiments. That's an 18-pound robot. We've got a bunch of those. We've got acoustic sensors on them, and we've done multi-vehicle experiments where we localize things that are underwater. The reason that is very challenging is because the underwater comms bandwidth is phenomenally low. For example, those vehicles right there can transmit 32 bytes every 10 seconds. That's the comms channel. So you have to really rethink how you do stuff. We also get some work just to build things, and it's really fun. This is a vehicle, this is a high-speed AUV. It goes around 15 knots. That's 7.5 meters per second. It's got a whole bunch of unusual design constraints. The Navy came to us and said, we saw you were building small vehicles. Can you build one that's even smaller and much, much faster? And we said, well, gosh, things don't scale linearly. We're not sure. They said, you've got an unlimited budget. And we said, we try really hard. So we did that in 10 months, from blank sheet of paper to that exact video, and $300,000. We thought that was really cool. Our sponsor had spent $3 million in 3 years on a contractor who had failed to do this. So why can we do stuff like this at Virginia Tech? Virginia Tech is up in the mountains, much like you are. In fact, we're in the same mountain range, just a different state. We are entirely landlocked. But we do have one of 4 graduate programs in naval architecture in the country. So as a control theorist in electrical engineering, I can put teams together of people who know all the stuff I have no idea how it works. Propulsion, hydrodynamic structures, all that good ocean engineering, naval architecture kind of stuff we have. And I can put teams together to do stuff like this. So real briefly, let me try to just summarize a little bit. We do, more recently, we were asked to build a vehicle that could self-moor. So we think this is a really good example of level-headed engineering. It needed to deploy an anchor. Well, the anchor is a false nose that's held on with a vacuum. We just release the vacuum and the whole thing falls. Sometime in the future, it's been programmed, or we communicate with it and tell it to release its mooring line. I'm talking faster than the video. Sorry about that. It'll come to the surface and either come home with a pre-programmed position, or it can communicate via SATCOM and ask for new instructions. Its entire energy budget is such that it can run a low-power sensor well moored for a year. So we'll move on. And the Navy liked that. More recently, what we're trying to finish up now is the Shepherd vehicle. It's the same vehicle where the mooring hardware was taken off, and we replaced better navigation equipment on it, along with a side scan sonar that allows us to do bathymetric mapping. The Navy has vehicles like this, but that didn't quite fill the specific niche that our version does. So they asked us to go ahead and turn it into something useful. All right, so let me get back to our actual project. Thanks for indulging me on that. So this slide is the theme to this talk. Why is this project interesting for us? We think we've got two competing things we have to solve. We've got a global map, global path type problem, an extremely large environment. We need to go somewhere. We've got a goal location. We need to generate a path. We think the challenge here is representation of this very large riverine environment. For sure, we cannot do this path planning in real time. So we know we can't use traditional path planning methods. The reason being is that our vehicle, unlike, say, a robotic car, slips. It slips like crazy. So when we do our planning, at least locally, looking ahead a little bit, we need to faithfully incorporate vehicle dynamics. So we're not just doing plans, we're creating dynamically feasible trajectories. We certainly couldn't do that over very large planning horizons. So we think we've got to somehow do both. Let me first talk about the left-hand side of this. I lied. Let me first talk about sensing. Just to give you a sense of what the vehicle's like. A robotic boat is pretty easy. I just saw one today, which has a whole lot of clever in it. Ours has no clever in it whatsoever. We bought a boat. We turned it into a robot. Any high school student can do that. The sensing is important for us. What we use is a laser line scanner that looks ahead of us, sees things on the surface. For those people that work on ground vehicles, I understand that a laser line scanner is a problem with puddles. You see sort of an infinitely deep hole. For us, that's perfect. We want to identify everything that's not water. So we couldn't ask for a better or easier sensor to use. We use GPS. The program that's running here has to worry about navigation. We don't. Our sponsor said we can use GPS. We're very lucky. And then we have to do subsea sensing. So our collaborator on this is the Naval Postgraduate School in Monterey, California. They are responsible for this forward-looking sonar. This sonar problem is hard. Here's an example of what the forward-looking sonar sees. They turn this into an obstacle map, things that we can run over and things that we cannot. And this is a challenging problem. I'll just leave it at that. They're the smart people that are working on it. OK, so we've got, we're getting sensor data that's surface and sensor data that's subsurface. We're creating an occupancy map out of both, and we consider it just a union map. If we see something in the surface, we populate our occupancy map with that information. If we see something subsurface, we also populate our occupancy map with that information and just update things in a very orthodox Bayesian manner. So no surprises here whatsoever. This is probably the most straightforward thing you can do. It would be neat if we could do something more clever. Say if we see something on the surface, we should predict there's something under the surface as well. That's harder than it sounds, and there are lots of exceptions. And so far, because we see so many exceptions, we decided not to do that. That it's unlikely to be a very fruitful path. OK, let me briefly show you some field trials. So this is quite a while ago now. We're working at the Pearl River. This is in the border between Mississippi and Louisiana. Stennis Space Center's there. We do this because the Navy has a special boat team that operates at this location. The Pearl River is somehow tropical looking, so this is a good place to test this. We went 6.3 kilometers downriver. We had inaccurate maps, and we had boats passing by. And we were bored out of our mind, which means everything worked well. So let me show you this to you. I think this will just run. And at this point, there we go. This is pretty pedestrian stuff. So the river's pretty wide. There are sort of discrete things we can run into. They're not hard to find. And what I'll be doing for the rest of this talk is showing you why doing more than this is very challenging and what we've done to set up the problem to solve more challenging areas in the near future. So it missed an island. Congratulations. This is a support for the I-10 bridge. that it wasn't in its map. It managed to miss the bridge support. Thank goodness. That would have been really embarrassing. And it goes on. So here's what the vehicle sees. So this is our occupancy map. And here's those bridge supports. You're seeing both surface and subsurface data combined. Our prior map is where it looks like a river, and the data we're getting in real time is the less structured data. You can see the river has shifted over time from when we took our map. So we've got a constant error. Here's that island. This is going the other direction now, that island that we didn't know about. And it's going to go on. I think there's one more section here just to show that it gets narrower and narrower as you go upstream. And because we're looking underwater, the shoreline isn't necessarily where we see it from the surface. OK, let me go forward. All right, so here's what I thought I was going to next. Long-range planning. So we don't have an answer, any sort of magic bullet answer for this. So let me just show you what we did. So we first started out by using a level set planning approach. And for some technical reasons, this seemed like a really good idea. We applied all this sort of the standard tricks you can apply to this kind of approach to speed it up, meaning our map is changing locally all the time. And usually that means that our path plan only needs to change locally. So when we're computing an updated path, when we're repairing our path, that can happen pretty fast, except for some pathological cases. And then we took this out, and this was running fast. This was great. We took this out to the field, and we found those pathological cases happened all the time. So this wasn't the answer. And part of the reason this wasn't the answer, or any class of solution like this, is really how we're representing the environment. So we've gridded up the river, and we're doing planning over this grid. So we've just got our planning space is just simply too big. Because the river is very narrow, we want our boat to get through parts of the river that are really no wider than the boat itself. Our discretization in some places, needs to be quite small. In other places, maybe it could be much larger. So maybe there's something to do here about adaptively sizing the grid. But in the end, this is an enormously large environment. I don't think that's really going to turn out to be the best answer. This turned out to be a good answer. So what we did was backed up and said it's not the planning algorithm that's going to make this. It's really the representation of the environment that's going to make this. So we came up with something called a skeleton map of our Riverine system. So it's a bunch of nodes running down the river. Now our map, our representation of the environment is very, very sparse. Planning is really fast. Not because we're doing anything clever with planning, just because our representation is so small. All right. Because this is something we did, let me just run through real quick how it works. So we start with some prior data. In this case, it's a Google map, but it could be anything else. And we create a binary image of where we think water is and where we think land is. So now this is safe and not safe. We do morphological thinning. That gives us the skeleton. We're going to get a few too many branches. We'll figure out how to prune some away, and we will do that. So those will prune away. And then we will attach nodes along this skeleton. And we will get rid of as many as we can. So now I've got a skeleton representation of my river with all these nodes. Attached to each node, I'll have a ball. And then the collection of balls gives me a smoothed representation of my river. And all this turns out to be data that we can use. Let me see. I'm afraid I might have forgotten one point. I think I didn't. We'll make it work. So at the end, we want to add another vertex for our goal location. We compute for each node. We have the distance from the goal location to that node, essentially making a road map. And we're good to go. We can do planning very, very fast. And this is an important part I wanted to make. At each node, I have distance to the goal location. I have cost to go. I had what I neglected to mention, that in this previous approach I showed you, where we were working with level sets, we also had the cost to go from every location. So no matter where I was, I could estimate, at least on this global approximate path, how long until I get to the goal location. That turns out to be important. OK, so back to this picture. So this is our main theme. So we've got this idea of a global map and path that is very sparse, so we can do planning on it very, very fast. Interesting to note, it can't always be repaired in real time. So any changes to our map are local. And that's good. That sort of bounds where we have to repair our map. But we aren't computationally fast. We haven't solved that problem. It still might take us 30 seconds, maybe, something like that. So we can't quite do it in real time. If we're constantly repairing this map based on new data, we're in trouble. So what we want to do is somehow delay this repair until we absolutely need to do it. And when we absolutely need to do it, there's no way we can get around not doing it. We'll stop and sit for 30 seconds and do it. OK, so that leads us to this local trajectory problem. So now everything we've been talking about is a path, not necessarily dynamically feasible. But I couldn't compute anything dynamically feasible anyways for a long path. I can only look a minute or two into the future to create something that's dynamically feasible. What I want to do, where we're going with this, is I want to compute a sequence of these limited horizon trajectories, combine global information in some sort of clever way so that I'm guaranteed that my sequence of local trajectories converges to the goal location. First of all, let me show you that the vessel dynamics really are interesting. So dynamics count. And the big deal is we slip. So any boat's going to slip. A shallow draft riverine boat's going to slip a lot. I can drive this with a 90-degree side slip. That means I can go sideways. That's great for docking, but not so good for control because you can't just choose to go 90 degrees. You've got to do some work to get there. OK, interestingly enough, the faster we go, the less we slip, so the better a linear controller would work. If we stop completely, if we hit the brakes, we keep going, of course. All right, so all this stuff counts. Let me move on. OK, so these dynamically feasible trajectories. Here is exactly the problem we'd like to solve if we could. So I've got an optimal control problem subject to vehicle dynamics. And I'm going to choose a cost function so that it's 0 at my goal location and has other nice quantities. I don't know exactly what it is, but it's going to look like this, maybe. And I want to solve this. Of course, I can't. And by the way, some technical assumptions. My integrand will always be non-negative. And I'll make a lot of little technical assumptions go away by just saying a solution to that exists. We'll take the easy way out for now. OK? So since I can't compute my optimal control for an infinite horizon, let me compute it for a finite horizon. This is all I can do. So for some horizon cap t, let me solve the same problem. Because I have a finite horizon, I also have the opportunity of throwing in a terminal state cost. So let me do that. There's no general form of this problem. And there I go. Let me solve this. All right. I want to do this in a receding horizon framework. So let me be a little bit formal about what I mean here. So we're going to compute our optimal control over some horizon cap t. I think I've got this all worked out. I do, good. So here's where we're going to compute that optimal control for. This is our trajectory generation planning horizon. I'm only going to implement it for some much smaller interval delta. And then I'm going to plan again distance time interval cap t. And I'm going to do this over and over and over again. This is the standard receding horizon approach. So this is how we do it. Does it work? Do I have any reason to think that if I just compute these optimal controls over and over and over again, and even let them overlap very nicely, that they'll work? Seems like they should. But they don't. There's actually no theory alone that's, for what I've shown you, that says this should work. And there's some nifty pathological examples that you can come up with that this turns out to be destabilizing. OK, so what does work? It turns out that the secret sauce for making this kind of stuff work is in the terminal state cost. There's a couple of directions we could go. One, if we make the terminal state cost 0, but we increase the planning horizon sufficiently long, everything's going to work out. So there exists a cap t that's going to make this work. It could be insanely large. I'm essentially approximating the infinite horizon problem. So that's not so useful to me. Another one is if in some meaningful sense that I will explain later, the terminal state cost is an upper bound for the cost to go. So the cost to go, let me explain that in a minute, but that's related to what was on these maps. And finally, There's number 3, which is this terminal state cost satisfies something related to a Lyapunov-like requirement, a control Lyapunov-like requirement, then things will work as well too. It turns out that if this is satisfied, then this one is. So this one's a little more general. Let me be precise. Let me go through each of these. So the first one doesn't matter. We're really not going to do that. We can't just make T infinitely large. But here's what we are doing. And here's why the terminal state costs can matter. So the infinite horizon problem I couldn't solve, but let me break it up into the finite horizon problem and the tail, the part I forgot. And so now we can see what the terminal state cost does, why we compare it to the cost to go. The part I threw out is the cost to go. Somehow, that looks like it could be related to the terminal state cost. So that there is some relationship isn't surprising. OK. So it turns out I don't have to be equal. It turns out that if this is satisfied, and a little bit more, then I'm good to go. If my terminal state cost, this thing I'm sort of representing the part I threw out, as long as it's an upper bound for the part I threw out, then my sequence of trajectories are going to be stabilizing. That's kind of neat. OK, let's look at this third case very specifically. So this is the control Lyapunov type case. And so we'll get asymptotic stability for the whole system if we meet that requirement. But then again, if we have a control Lyapunov function, then this turns out to be true. So we have an upper bound for our cost to go anyways. So number 3 didn't turn out to be that useful to us. Oops, sorry. Let me skip that. All right, so this is our 2 sort of results we have from the analysis I showed you so far, being mostly specific, with dropping a few little details here and there. If for every I, that's our index on these trajectories we generate, if these conditions are met, either one of these, the control Lyapunov one or the second one, which is the related to an upper bound for the cost to go, then the integrand from our cost function goes to 0. If I've chosen that integrand correctly, the only place that happens is at the goal location. So I'm good. That's all I really need. And let me be precise. The only place 1 or 2 need to be satisfied are at the end. So this is kind of interesting thing. Our implementation interval was delta, way over there. We only implement for a little while, then we recompute and implement again. At the end of that planned trajectory, for an interval of length delta as well, I check if either one of these are satisfied. If they are, then I'm good to go. And I'm going to get to the goal location. So what does this do for us more practically? All right, so here's what we're really doing. We've got some position. We've got some notion of a global path. And we need to compute an actual trajectory. So there's a local trajectory I might have computed. I will go ahead and do that. I will check the matching condition. And I'll show you a little bit more about what the matching condition means physically. I'll check them. If they fail, well, that's bad. I need the matching condition to work. So there's a couple things I could do. One, I could just increase the planning horizon, the cap T. In fact, we do that. The other is we could do a global update, a global map update. That's the interesting thing we were looking for. So we couldn't sort of repair and keep our global information consistent and correct at real-time speeds. So what we do is just delay it until we absolutely positively have to update it, and then we'll do so. And what we find in practice is that we don't have to do this very often at all. This is one of those cases where the pathological case doesn't show up much, and it was really nice. In the example I showed you in the beginning where we're running up and down the Pearl River, we never updated the global map. When we had a problem, we increased the planning horizon T. So what does that mean? That means our global map was roughly consistent with what we were seeing. And if I saw something bad, it was a local phenomena. If my planning horizon is extended, then I'm essentially doing obstacle avoidance around it. I get to the other side of that bad thing, and I'm now more consistent with my global information. I can go ahead. I don't really have to update my global information. We like this a lot. We thought this was a good idea. So we get obstacle avoidance, and we get delay of global map updates. Let me show you what this means in a couple different contexts. So in that control the op and off context, this turned out to be real consistent, had some nice properties for this original level set approach. And ignoring all sorts of details, when we get to the end, it turns out that matching condition was an angle condition on the path from the global map and the path of the trajectory that we planned, the dynamically feasible trajectory. So at the very end of this dynamically feasible trajectory, we compare the angle of that trajectory and the angle of the global path. And as long as they weren't really far apart, we were probably good to go. Let's see that. So now we have some real field data to demonstrate exactly that phenomena and see how it works. So this is local to Virginia Tech. So we've got a large hydroelectric impoundment of the New River. It's about 4,500 acres. It turns out to be not a bad place to do tropical riverine studies. Here's what it looks like. That doesn't look entirely dissimilar from Stennis and the Pearl River. So what we did was we looked at this little cove. We started inside the cove. We just need to get to the other side of the cove. To make sure we were doing things in real time, we erased that peninsula from the prior map, so we had to find that in real time. OK, so here we go. So this is real data from our boat. We've got a GOA location. We've got our unmanned surface vehicle. We've got anything that's gray is land from our prior map. Anything that's white is shoreline. It's things we're finding in real time. Anything that's gray is, well, we're not clever. We put a buffer around what we think is land so that we won't get too close to it. At least we were doing that here. OK, so we've got a global path segment. So I've used this level set approach to compute a global path. Of course, global doesn't mean much because it's not very far away. But it's going to demonstrate what we want. And then I've got a local trajectory. OK, so interestingly enough, our global path goes right through the land as we are beginning to discover it. The USV doesn't seem to care. It goes ahead and computes a trajectory that goes around that segment of land. But interestingly enough, it does not require a global path update. And it doesn't look like it's following the global path. And it probably shouldn't. But it turned out this it was not so far off that it generated a global update. So it just keeps going. And everything's going fine. We're not touching global data. And we keep going. And we're finding more of the peninsula. And still no global update. OK, now we found the rest of the peninsula. There's no way through. So the purple line, which is the trajectory we generate, our local trajectory, has to go the other direction. OK, at this point, it turns out, well, we can't tell it by staring at it, that we're going to need a global path update. What's going on with the matching condition fails, and we're going to update the global path. So now the global path is going to go around the peninsula just like the trajectory will, and we'll work our way to the end. The lesson from here is we can use stale global maps for a long time. And in practice, and other things we've seen for hours on end. OK, so just very recently, we've begun asking ourselves, so exactly what are we doing with this cost function? I haven't told you much about it yet. And we've been sort of using stuff that made sense, but we weren't exactly sure what it meant. Here's what we've been doing. This integral cost is essentially path length weighted by whatever's in the map. And that seems like a good idea. So the map is sort of more costly where there's objects, less costly where there's not. So we take our path and weight the length of the path by whatever's on the map. That seems like a good idea. It will keep us from going through obstacles. It seems like in some we're minimizing risk in some way. And then similarly, we get the same type of information from the terminal state cost from the global map. All right. What we want, however, is the probability of no failures. That's really what we want. We don't want to run into stuff. So what's the probability of running into something? It's not integrating the path over my occupancy map. So what is it? It turns out that we can get exactly the probability of no failures if the value of the map at each location is in units of failures per unit distance. By failures, I mean running into something. So if I found it, if my occupancy map shows an obstacle, I would expect my failures per unit distance of that location to be very high. If I haven't found something, I would expect my failures per unit distance to be low, but never 0, because I'm going to have failures from all sorts of sources, and I'm going to miss objects at times. OK, so if my map is in these units, then I can write down an expression for the probability of no failures along a path. And then I can go ahead and rewrite my cost function. So it's precisely, I'm optimizing precisely this. What is the probability of mission success? I'm going to choose paths that make this as good as possible. So we really end up with log probability of failure and log probability of global map. But everything turns out to be consistent. What is our matching condition in this case? So the matching condition is this thing we have to satisfy at the end of every trajectory. In this case, speaking loosely, at the end of every local trajectory, that last segment, is at least as safe as the corresponding global path segment. So I think in practice, we haven't done this in practice yet. We just kind of worked this all out. I think in practice, what this means is you look at your map globally and you make some broad assumptions about what's there. Locally, and you've got to sort of make your assumptions so that locally it's possible to do no worse. OK. A few more details. So I've told you a lot about how we do the guidance problem, but as an organization like this knows a lot about putting autonomous vehicles into the field, there's a few things I've missed, like the control, modeling, everything else. So, and I'll do this very, very briefly. So for the USV, we spent some, Professor Craig Woolsey at Virginia Tech and his student Christian Sonnenberg did a lot of work with modeling of USV. The model turns out to be fairly simple, sort of the simplest thing that will incorporate some side slip. So ignoring details. And then now that we have a model, we can compute dynamically feasible trajectories. And how do we do this? I would love someone from Carnegie Mellon to tell me how to do this well. Instead, I will tell you how we did it. We found this really hard. We spent I had a postdoc who spent much of his time, over a year and a half, trying to figure out how to make this work. So we want to solve that optimization problem over our occupancy map. When we finally found a solution, after trying a whole bunch of standard approaches, this is really all we learned. Make your search space as small as you possibly can, and pick a darn good initial condition. And that turns out to be good enough. And so now we use an A-star variant to get an initial condition, and then we turn the whole thing into a nonlinear program and use Hook-Jeeves optimization to actually get a dynamically feasible trajectory. We can do that in about 30 milliseconds. So we can do it very, very fast. We also need to be able to back up. So again, super briefly, let me just mention a little bit about how this works. We want to back up. Oh, shoot, that's making our search space larger. I don't want to do that. So we use the same theme, which is make your search space as small as possible. So backing up for us is a single backward motion followed by something going forward. So the only question is, how long do you back up? So when we back up, first of all, we back up as little as possible. I want to mention that's consistent with human boat drivers. Boats don't do well going backwards. So all of us want to back up as little as possible. We only do it when no forward path exists. We first pick a local goal, and we generate a candidate backward trajectory. And for that backward trajectory, we'll have a feasible forward path at different locations. And this corresponds to picking how long do we back up. From that, we pick the very best, and we move on. OK, so that's the trajectory generation problem for us, solving the optimization problem. How about control? So now we've got trajectories that we know our vehicle can follow. So we need a control system that should allow them to do this. Because we've picked a dynamically feasible trajectory, we are doing control about that trajectory. It ought to be a not insanely difficult problem. All right. Now looking at this, one might think I'm showing you an awful lot of confusing data. Surprisingly, I'm showing exactly what you should see. So let me try to explain it as quickly as I can. The reference trajectory is in black. So that's the dynamically feasible trajectory we want the boat to follow. The circles are constant time points. So when the circles are far apart, the boat's going fast. When the circles are close together, the boat's going slow. So we're regulating speed as well as position. The green is a backstepping controller that Christian Sonnenberg came up with. The red is a standard PD controller that we use. And we use this controller a lot. We can't use it for very aggressive stuff. Now, as a controls person, I look at this and go, I don't believe you. You are not comparing apples and apples. I can't demonstrate it in one slide, but I will attest to the fact they did a ton of work to do their very best to compare apples to apples. And this controller really does work phenomenally better than a PD controller or a PID controller when you ask for aggressive maneuvers. The kinds of things that it works well for that are very surprising is when you're speeding up and then you slow down, what happens is your wake catches up with you and your boat really moves a lot. And it sometimes moves left or right. You never know which one. And this controller manages that really well. Where the red line goes crazy, that's exactly what's happening. And totally, the PD controller can't even begin to manage that. OK, so, but where I was trying to claim that we did compare apples to apples, let me do truth in advertising and say there is some stuff missing from this. Although this controller works really, really well, we don't have a good handle on why. So one of the really interesting things left for us is why does this controller work so well? Works much better than it should. All right. Seemingly a different topic. So we got everything running, and we took it to the Navy, and they really liked it. I mean, it's not doing everything it needs to do yet, but it's getting there. And they said, boy, that's really fantastic. We'd like you to keep going and getting this ready for us. But we're a little worried because we're going to be the people who are going to end up babysitting your boat, and we don't want to do that. What can you do to convince us we're not going to have to babysit your boat? I don't know if you've heard that before, but I think they're absolutely right. An autonomous vehicle that can really go out in the wild for days at a time, I don't think we're doing that yet. And the operators who are out there who have to manage these things look at them and go, that's a huge workload for me to keep on top of this the whole time. So we looked at how we could transition some technology before we were able to demonstrate all of that to them. So this is what we did. We called it the helmsman assist system. But we took the entire sensing and autonomy package and hooked it up to one of their boats, minus the autopilot. So we didn't inject anything into throttle or rudder control. We're essentially building maps and paths and doing it in real time, and came up with a display they could use. And the idea was that these operators need to work at night and all weather. And if we could provide them a display with both a map and suggestions on where to go, they would find this useful. So we demonstrated this last September now. And it turned out to be pretty useful. And here's why we think that. Because the operator who doesn't really want much to do with new technology wouldn't look at our display for the first hour. But by hour number 3, he was doing nothing but looking at our display. And we thought that was really cool. So this is an example not of robotics, but how we can take a robot technology and transition it quicker and get people to be a little more comfortable with what we're developing for them. All right. Concluding remarks. Let me just have this video running while we're doing this. So essentially what I've showed you is contributions to very long-range guidance problems. Where we're going next is we've learned a little bit about this helmsman assist system, and we're going to go back and show them a little better version of it. Our next step for really where we're going is to demonstrate our system in a really demanding environment for a long time. We feel we have all the pieces running. We really want to get it up into the upper Pearl River where there's just so many more obstacles. Everything's harder. The boat's going to have to back up a lot. It's going to break. We don't know where. We're kind of excited to give it a shot. Let me conclude with Acknowledgement. So this is funded by ONR. The same sister project is being funded here. Dr. Aditya Gadre is the lead postdoc. Craig Woolsey is the co-PI, and Christian Sonnenberg and Xu Du did an awful lot of hands-on graduate student work. Our colleagues at the Naval Postgraduate School have done a ton to make sure we can do these experiments with the Navy, but also with a forward-looking sonar, and we're very grateful for that. So I'll conclude here. Thank you very much.
I noticed a lot of the engineering challenges we're facing, which also kind of spilled over into your very controlled design. Were things like issues with maneuverability, including various speeds, issues with the weight catching up to the boat, you're balancing many things along these lines. Have you considered a catamaran hull? Since, frankly, cats often have much greater efficiency at the same speed than monohulls for the amount of drag. They're very maneuverable at low speeds. They can practically turn all Dynamically in case of a diff drive. They actually produce much less weight because they're thinner hulls, and basically what's very challenging to engineer, they often tend to do better than monohulls. So you consider a different hull?
But we haven't.
Okay.
So, and not for a specific engineering reason. We had reason to buy something that looked like what the Navy was already using. And then once we did that, we're the direction we're going.
You were talking about finding the probability of failure at each cell. How did you determine that probability of failure at some place? Was that the distance?
That's a good question, and maybe I didn't talk much about this. So the challenge that we were trying to address is where are we making assumptions and where are we rigorously doing stuff? And when we were computing a trajectory over our occupancy map, it seemed like we were doing the right thing, but it was all made up. And so by reformulating the problem, being more precise about how do we actually minimize probability of failure, we're being precise about part of it. Now, to answer your question, what's left over is we have to make up or have engineering judgment about what values actually go into the map. But I feel that's good because at least we know precisely where we're applying engineering judgment and where we're actually doing things that are formally correct. I like that.
In your example of your control, the reference path was like this, looked like oscillating. Is that actually recognized as an optimum path, or is that example to show your control algorithm?
That was an example to show our control algorithm.
Oh, I see. So in a real optical path is probably like this.
We think optimal paths will get really messy as we get into increasingly complex environments. So we think that
if the river is somehow has a obstacle.
Yeah, because we think this is really wide right here, but the place you can go through turns out to be really small. And you can't tell from our forward-looking sonar until you've been staring at it for a while. So we expect to be nosing up and then backwards and going around, and we don't expect to be having anything as pretty as this.
What was the range and what was the power source for that little thing you showed at the beginning?
Oh, the
high speed?
The high speed? Oh, gosh, I don't know range. Endurance is like 8 minutes. So.
And how was it powered?
For us, it was lithium polymer. So for those that don't know, power underwater is the cube of speed. No, speed, yeah, cube of speed. So as the faster you go, the power requirements go up really, really fast. So 8 minutes is a long time.
In the binary map we showed you as a prior map to plan for the global map, you created a graph like structure through that binary map to show the nodes, I guess. How
Yeah.
did you do that? Manually or?
No, that's automated. So there's this morphological thinning operation. It's an image processing operation that creates that skeleton. And then there's a procedure for placing the nodes so that each one is visible to its neighbor. And probably some other details I don't recall.
A bit more on speed. Longrange, what was the typical top speed of the boat? What's your typical operating speed in the common case?
Yeah, so what we're at right now is 5 knots, which we consider slow.
Okay.
We'd like to go much, much faster. So that's why sort of we set in place what we have so we can eventually get there.
Okay.
Top speed for our boat's about 20 knots.
Okay.
Top speed for our underwater sonar is 10 knots. So there's a speed limit on the acoustics. So with that sonar, we're not going any faster. The Navy is investing in sonars that we might be able to go faster with.
In the tropical river problem or task, what are the things that eventually the boats need to sense and record?
We don't want to know.
Oh, okay.
But we understand that if we can get to a goal location and back, and perhaps also additionally solve an exploration problem that I think Sebastian's group is more interested in, that those are all good things. The kind of data we'd like to bring back, we believe, is a map of where it is safe to travel. And that map should show every place where it is deeper than, I don't know what number of, 50 centimeters, something like that.
So in that sense, your robot's task is basically mapping.
Yeah.
A bit more on the cost function, I think of hazard or failure per unit length. Do you have any sort of inherent code for like catastrophic failure? Like this is an extreme case, boat goes off waterfall, hits strong rapids, completely destroys the thing.
Yeah.
Do you have any sort of way to code that into your planning algorithm?
You mean, well, that would be places you absolutely can't go, right?
Pretty much, as in if you went there, planning would become a moot point.
Right, right. So I mean, so the largest integer you can fit,
Okay.
you know, that kind of thing.
Gotcha.
Sorry, in your example, you showed a case where you had pretty good priors from aerial imagery, which is reasonable, and you also showed recovery from a case where the prior was wrong. Just curious, and it touches on this, you just mentioned exploration. How do you think the approach you're using would work when the prior is really not that informative, so that everything might be something on that?
What will work when it's?
When the prior isn't that clear cut, that really, you couldn't, maybe the binary classifying isn't really very
Yeah,
much of an option.
I'm not sure with what we have set up now, with what we were doing maybe 2 years ago at this point, where we had cases like that we tried to run through. The performance was surprisingly bad. So because you wouldn't know the shoreline, you'd be discovering it as you went. We can look forward about 150 meters. We'd be discovering it as we go, and we'd essentially bounce along the shoreline. And maybe that's okay, maybe that's the best you can do. But those are the kind of behaviors we would see.
About when you had to back up, and you said you found a feasible backup trajectory, picked a local goal, and then I guess sampled along the backup trajectory and planned to the local goal.
Right.
If you're in a really complicated environment where perhaps you can't execute, there's no feasible single backup, maybe you have to zigzag, I feel like that would break down. So how do you pick the local goal?
We don't know how. So if that happens, we can't address it yet.
Okay. How do you pick the local goal right now?
Honestly, I don't know. I mean, sorry. I mean, there's nothing clever about it. I'm sure, but just something off, something near the global path at the edge of the map.
Have you considered including in your dynamics model that phenomenon you're talking about when you slow down and the weight catches up to you?
Turns out we didn't have to because the controller managed it pretty well.
So you have the state feedback's really good.
Yeah.
Then this morphological operation, it seems like what it comes up with in the end is a Bornoy diagram, right?
Yeah.
Because you basically get the middle of the path, and like in a discrete fashion, and this finning and so on. It seems like in the end it comes up with a moment.
I bet it's not exactly that, but that might be a much quicker way to get it.
Yeah, and there are some incremental ways of getting them on the river maps.
That's very good.
Just out of curiosity, what was like the coolest success that you experienced and worst failure that your boat occurred?
Worst failure. I mean, it's hard to rank the failures. They're just, just keep track of them all.
Don't forget the coolest success.
Yeah, so the coolest success. You know, the experiment where we found ourselves bored. So running down the river for 6 kilometers and back. So our definition of success in autonomy is the operators are bored. And so we realized that we had been successful.
What about the failure?
Well, like I said, there's so many that I can't rank them all. But you know, like I'm sure you do, you design for the failures you can enumerate. So our sonar boom was carefully designed to have a quick release. So if it ran into something, it would pop up. So we actually had no terrible, you know, we didn't, in the underwater domain, our sense of risk is much worse. When we release our vehicle, it disappears on purpose. And our heart stops, and we hope to hear from it soon. For the surface vehicle, we're watching it the whole time. If something goes bad, we press the red button. So our sense of risk is different, and things don't go really wrong when you can do that.
For the line scanner in the gimbal, which you mentioned was so effective for distinguishing water surfaces from land, in terms of the resolution, could it be so sensitive as to detect like sea state if need be, like different elevations or swells in the waves if need be, or is it not so good for that?
I would suspect it's not good for that.
Okay.
I think you only get a return from water if it's a fully orthogonal surface.
Okay.
Thank you.